Good. So now that we've explored a bit of computational examples with determinants, we're going to look at some of the properties of determinants. We're going to look at some of the reasons why determinants are useful, right? We're not calculating these things for nothing. There are reasons that people care about determinants. We did see in the introduction that they do have something to do with solutions to systems of equations. But we'll see that determinants will sometimes tell us things about the matrices that we're computing the determinants of. And that's what we want to look at here. Okay, so let's look at, well, what happens when you multiply a matrix by a scalar? What does that do to the determinant? Okay, so we do know that if we multiply one row of a matrix by a scalar k, that multiplies the determinant by k, right? What happens if we multiply every row? Right, what do we know about the determinant of k times a? So think about this. So k times a is going to be, okay, so it's ka11, ka12, all the way down to ka1n, ka21, ka22, ka2n, okay, down to kan1, kan2, kann. Okay, well, we know that you can, if you factor a scalar out of one row, you get a k out front of the determinant. So let's take determinants of these things, right? So if we want the determinant of ka, then I should do vertical bars here. Okay, so if we take k out of the first row, we would have a11, a12, a1n, and then ka1 or a21, and then oops, ka22 over to ka2n, right, down to kan1, kan2 over to kann, right? But then, of course, I could factor the k out of the second row, and I would get k squared, and I would have a11 over to a1n, a21 over to a2n. But everything else still has that k in there. Kan1 and n, right? But I can keep going. I can take k out of the third row, the fourth row, and so on down to the end. And so once I get down to the bottom, how many times did I have to take k out? Once for the first row, once for the second, once for the third, in total n times. K to the n times, well, what's left after I factor all the k's? A, determinant of a, okay? So there we go, that's our property. The determinant of k times a is k to the n times the determinant of a for any scalar k. All right. So notice that this very much depends on the size of the matrix, right? The number of rows tells you what power you need. Okay. So there's one basic property of the determinant. Now, we're going to look at determinants of elementary matrices here because we want to build up to an important result, which is what happens when you take the determinant of a product. Now, there's a few things that we know. One thing we know is that the determinant of the identity matrix is 1, right? Because, well, it's a triangular matrix with 1s down the diagonal, so if I wanted to calculate the determinant, it's 1 times 1 times 1 times 1. It's 1. Okay. Now, every elementary matrix is obtained from the identity via a single row operation, right? So if I do a row operation where I exchange two rows, okay, and I get down to some other elementary matrix, let's call this one E1, okay, then what is the determinant of E1? Well, it's minus the determinant of the identity, so it's minus 1, okay? If I do a row operation where I multiply one of the rows by a scalar k, getting me down to E2. I know that the determinant of E2 is going to be k times the determinant of I, so k times 1, which is k. And if I do the type of row operation where I add a multiple of one row to another, okay, a type 3 row operation, and that gives me an E3. Well, I know that that type of row operation does not change the determinant, so that guy must have determinant 1, okay? So we know what the determinant of every elementary matrix is, right? We also know that multiplying on the left by an elementary matrix performs a row operation. And so one of the things that we can see right away is that, think about computing the determinant of a product. Well, let's just do it for 2, right? Think about, and these are, let's, maybe I shouldn't call them E1, E2. I don't know, let's call them E and F, maybe, where E and F are elementary matrices, okay? So let's say I have two elementary matrices. Well, I can think of it like this, right? I start with I, okay? I do some sort of row operation, which gets me to F. I do the row operation used to create F. Then I do the row operation used to create E, and that gets me to E times F, right? And how does the determinant change? So the determinant here we'd have determinant 1. That's not a good way to write it. Let's just write the determinants along the bottom, right? So determinant of 1, and then that's going to go to, well, depending on the type of row operation used to create F, right? It could be minus, could be the same, it could be minus 1, it could be K, right? And so then we figure out which one it is there. We figure out, now we do the other row operation, right, to get down to E times F. And what is the combined effect? Well, the combined effect is, let's say this is type 2 with a K, right? Then this guy here is going to be K, and maybe this one here is a type 1, okay? So exchanging two rows, and then I would know, well, that changes the sign, so I would get down to minus K, which is minus 1 times K. And what is minus 1 times K? This is the determinant of E times the determinant of F, right? So, and you can see that this would work if I did several row operations with several elementary matrices, right? If I had a product of elementary matrices, the determinant of that product is going to be the product of the determinants. And we want to see that this actually works in general, okay? So we want to work out that the determinant of A times B, or so written in terms of the vertical bars, determinant AB is determinant of A times determinant of B, okay? We're going to prove this using elementary matrices, but just to kind of give us a warm-up, give us one example to see that it's, of course, one example does not prove the result in general, but it gives us some evidence that things might be true. So 2 times 5 minus 1 times 3 is 13. Determinant of B, minus 3 times minus 2 minus 4 times 7, 6 minus 28, that's minus 22. Okay, there's going to be big numbers involved here. All right, so let's see. So determinant of, so let's first do the product, A times B, okay. 2 minus 1, 3, 5, minus 3, 4, 7, minus 2. So we multiply those out. Minus 6 minus 7, I get minus 13. Then 8 plus 2, I get 10. Minus 9 plus 35. 35 minus 9 gives me 26. And then 12 minus 10, I get 2. Okay. So there's A times B. So what is the determinant of A times B? In this case, the determinant of A, B, it's going to be, so minus 13 times 2, that's minus 26, subtract 26 times 10, minus 260. Okay, well, let's pull out that minus 26. Minus 26 times 1 plus 10. Minus 26 times 11. And 26 is 2 times 13. So I could do this as 13 times minus 2 times 11. That's 13 times minus 22, which is the determinant of A times the determinant of B. All right, so it works in that example. Why does it work in general? Well, the argument is using elementary matrices, okay? We look at two cases depending on whether or not A is invertible, okay? And we'll get one other result for free here, which is that the determinant of a non-invertible matrix is 0. If A is not invertible, the determinant of A must be 0. All right? Why is that? Well, if A is not invertible, we can apply a series of row operations represented here by elementary matrices E1, E2, down to EK. That gets us to our row echelon form, right? Or I guess these ones get us back, right? So the idea here is you would do same as this algorithm for writing an inverse as a product of elementary matrices. You do your row operations to get down to the reduced row echelon form. The inverses of those row operations tells you how to get back to A. So we can definitely write A like this. Now, if R has a row of zeros, okay, then when I multiply by B, R times B will also have a row of zeros, right? Because when I multiply by that row of zeros, I get zeros all the way across. So the determinant of R times B is 0. And now we realize that, well, for both the determinant of A and the determinant of A times B, right, we can get those guys from the determinants of R and RB using elementary row operations. And we know that when we do those elementary row operations, at most we're either changing the sign or multiplying by a non-zero constant, and none of those is going to change the fact that those determinants are 0, right? So the determinant of A times B equals 0 in this case, and of course 0 times the determinant of B is 0. So it works in that case. If A is invertible, then A is a product of elementary matrices, right? And so then what we do is we say, okay, so you kind of start with, we start with, on the one hand, we do A, and then we do our row operations. We get to E1A. Well, actually, sorry. On the one hand, let's do the identity first. So we start with the identity. We do E1 times the identity, E2, E1 times the identity, down to EK, E2, E1 times the identity. On the other hand, we can do B, right? And this is just equal to A here. We can do B. We do E1 times B, E2, E1, B, and so on down to EK, E2, E1 times B, which is A times B. Okay, and so then what you basically say is, all right, so the determinant of A times B is going to be, well, I start with the determinant of A, and then I keep track of the effect of these elementary row operations, and that's going to give me the determinant of A times B, right? But that's the same thing as starting with the determinant of the identity and keeping track of those same row operations and getting down to the determinant of A. And so again, you can basically, by looking at the elementary matrices or using the fact which we kind of argued at the beginning that the product rule kind of applies in the case of elementary matrices, you get that the determinant of A times B is the determinant of A times the determinant of b. And we'll see that this product rule has some interesting consequences in the next video.